To solve a linear regression problem, we are finding what's called the least squares approximate solution. What does that mean? We are generally given a system, ax equals b, that is inconsistent. There's no answer. It is not possible for me to make this vector b using the combination, any combination of those columns of A. So instead, we try to find the next best thing. We try to solve the closest problem to our original one. And the closest problem to our original one is this one, where we solve ax equals b hat. And b hat is the orthogonal projection. So this x hat is our approximate solution, and that's the thing that we are looking for. We want to get this x hat, and to do that we would solve ax hat equals b hat. But that's going to require us to find this b hat. So rather than starting with a system, trying to find a b hat, and then solve another system, can't we just solve one thing from the beginning and be done with it without having to form the b hat? Yeah, we can. So we're going to take an alternate approach that avoids building b hat. So it avoids b hat. And here's the idea. Since b hat is in our plane, so this kind of thing again, we've got our w, we've got our original vector that we can never create from our pieces. So instead we do this projection. Since b hat is in that plane, that means b minus b hat is orthogonal to the plane. And if it's orthogonal to the plane, that means this vector b minus b hat must satisfy A transpose x equals 0. We talked about this before. This vector right there is perpendicular to the plane. It's orthogonal to the plane. So therefore, it must be an answer to this other system, A transpose x equals b. So that means if I were to plug it into that equation, it must be equal to 0. So I can just go ahead and distribute things as I normally would. And the point of the story here is that anytime I see b hat, it is the result of my least squares solution, the thing that I'm trying to find. And that means I can just plug it into here, and I'll get A transpose B minus A transpose A x hat. And that all has to be 0. And so the point of the story is I have a new system that I can solve to get the same answer. So this is a new system that gives the same answer, x hat, without finding b hat. And that's kind of convenient. So without finding b hat first. These are called the normal equations. Math people like it because it avoids a lot of these extra steps. I don't need to find b hat. I can just start with the a that I've been given from my system and the b, the original vector that I've been given from my system. Nothing else to do. And this is an important result in your text. It's called proposition 6.5.4. The least squares approximate solution to the original problem ax equals b also satisfies these normal equations. And that's good. So rather than working with the original problem, I can work with this problem instead. It will give me the answer to the system that I'm looking for without having to build b hat. So time to go back to our original example. So in our original example, the system that we had was inconsistent. And the system that we had an A that was 1, 1, 1, 1, 2, 3, 5, and 6. The x hat was made up of the two parameters we were looking for, and the b was 3, 2, 1, 0. So now what we are going to do is we are going to solve this other system, A transpose A x hat equals A transpose B, to find our least squares best solution. So to find this least squares best solution, we need to form the transpose matrix, which is nice and easy to do. Transposing a matrix is very fun. We need the right-hand side, A transpose B, which means we're going to have to do this matrix vector product, which is also very easy to do. If you sit there and you do that matrix vector product, you're going to get the following result. This is a 2x4 matrix. This is a 4x1. You should expect to get a 2x1 matrix. These dimensions are compatible. You'll end up getting a 6 and a 17. The other thing we need is this matrix A transpose A. Now, this matrix A transpose A, also, you have to make sure that the dimensions are compatible. It will always be the case that this will be true. You can always form this matrix from any matrix you begin with. You will always get a 2x2 matrix. You can pause the video, spare yourself a little bit of the work here, or watching me do the work. You're always going to end up with this. One of your homework questions was always to show that A transpose A is always a symmetric matrix. Symmetric matrix means that the diagonal entries could be different, but anything off the diagonal is kind of reflected. Those are going to be the same. So now let's solve A transpose A x hat equals A transpose B. A lot of chatting, a lot of talking, but essentially what it boils down to is just solving a system. This is the system that I want to solve. And if I want to solve this system, it's pretty easy, just because the numbers here are doctored. So -4 times that first row is going to give me a -16 if I add it to that. Everything will work out in this particular case. And I'll end up with this. I can do another row reduction here. Now, in general, when you do this kind of thing, you shouldn't expect air quotes nice numbers. Everything's going to work out to give you whatever it gives. And in this particular case, these are the two values I'm going to end up with. -43 over 10 and 43 over 10 and -7 over 10. So the approximate solution, the least squares approximate solution, the thing that I want, is a vector that holds two constants, two unknowns, the y-intercept of the line and the slope of the line. And I just found it, 43 over 10, -7 over 10. So that means the line of best fit. The line of best fit is y equals mx plus b. And in this particular problem, that's going to be -7/10 x plus 43 over 10. So the attached PDF that I have given you gives you a sense of how that line looks with the data points graphed nice and precisely, but you can see it does a pretty good job. Now, one way to measure the error here, which is basically the distance of how long my original vector b is from the b hat. Now, the whole point of solving these normal equations is basically to avoid finding this b hat. But if you wanted to, you could do that, and you would find that this b hat is a 10th, 29, 22, 8, and 1. Generally, I don't recommend that you do that, but basically what you would find is that this thing is 1 over root 10. We aren't going to focus too much on the error here. It's just a number, and generally the smaller this number is, the better. However, we are going to be focused really on just getting these coefficients. Now, is this line unique, right? Could there have been another line that I could have chosen that would do a better job? We can't answer that generally, but we can try to give some conditions on when we may see uniqueness. And to try to get you there, I'm going to say, okay, this matrix A transpose A appears in our normal equations, and it's basically the left-hand side. So let's talk about this, because remember, uniqueness is related to linear independence. And so what we want to know is, does this system, the left-hand side of our system, what kind of pivot structure does it have? And I don't want to have to talk about it case by case. I would like to say something general about it. So that means we have to talk about this homogeneous equation. So if I take this homogeneous equation and then I dot it with some x, the same x that I've got there, remember that x dotted with any vector that's 0 is always going to give me 0. Remember that a dot product could be written as a transpose. And then remember transpose properties, that this is really AX transpose times AX. And that, of course, is then just another way of writing a dot product. So these two vectors have to be 0, or the length of this vector squared is 0. Now, way back when we talked about dot product and the first properties of the dot product, what you find is that this thing, the length of a vector can only be 0 if the vector itself is 0. Okay, so far what we've got is that solutions of A transpose A x equals 0, they also satisfy AX equals 0. So that's kind of good, right? If you can solve that homogeneous equation at the beginning, you will solve this AX equals 0. And now that we've got this thing, that means we've got this final result. So here's where we can impose some conditions. If A has linearly independent columns, that means we have the trivial solution only to AX equals 0. So if we impose this condition, that means A transpose AX equals 0 also has only the trivial solution. And if that's the case, that means then that the solutions to A transpose AX equals whatever vector on this side are unique. And that's what we're looking for, right? We want to make sure that the equation of this line that we find is unique. Well, the only way we can do it is by imposing this condition. So if the columns of A are linearly independent, then we get a unique least squares solution from the normal equations. And that's going to be important because in the next video, we're going to talk about how to do this system in a different way that will require this.